Hello everyone, I am Dr. Leena Chandra, Assistant Professor, Research Center of Physics, Fatima College. I am going to present an e-content on transmission electron microscope of MSc Physics program. So to explore microworld, many inventions have been devised. One of them is optical microscope. Human eye can see and distinguish small structures up to 0.2 millimeter. So beyond that, if you want to distinguish structures, we can see you make use of optical microscope. Optical microscope use light source as the illumination source. Therefore, it has its limitation. And only the structures are of the order of wavelength of light can be distinguished. And therefore, since the light wavelength is 400 nanometer to 600 nanometer, we can able to distinguish only microstructures up to that order. To break this point, engineers like Ernst Ruska from Germany, he has invented a device which is electron microscope. Electron microscope use electron beam, that too highly energetic electron beam as a source of illumination. Therefore, we can able to distinguish even atom, that is the atomic arrangements can be easily in a material can be easily seen through the electron microscope. And this electron microscope is nothing but it's a scientific instrument which uses highly energetic electron to examine very fine scale objects, and therefore topography, morphology, composition of details can be found for any material. And the resolution is very high, of the order 0.2 nanometer, and the magnification is 5 lakh times more than that, and it is very much higher when compared to optical microscope. There are two different types of microscope: transmission electron microscope, scanning electron microscope. Transmission electron microscope form images using electrons that are transmitted through the specimen, whereas scanning electron microscope utilize electrons that are bounced off the surface of the specimen. Let me explain this with the specimen interaction in electron microscopy. Incident electron beam interact with the atoms in the specimen, and there are these reactions happening at the top of the specimen. They are backscattered electrons scattered about 180 degree, and secondary electron, this is when incident electron interact with the atom, the electron which is in the lower energy orbit, that is the Casual orbit, it gets excited and it gets ionized, and it comes out as a form of secondary electron. And during this process, there will be a vacancy produced at the lower shell. In order to compensate, a high energy electron comes to the lower energy electron, and therefore it emits Auger electron, and this surplus energy can be emitted as a form of X-rays. All these happen at the top of the specimen, and they are utilized for scanning electron microscope, and that too for a bulk or thick specimen. Whereas the transmitter electrons sometimes may not interact with the atoms in the specimen, and it is unscattered electrons are produced, and some may get scattered as elastically and inelastically. These two are useful to form are useful in transmission electron microscopy to analyze a thin or foil sample. So as I said, the unscattered electron does not make any interaction with the atom of the specimen, and therefore it is used to find out the sample thickness, specimen thickness. Thicker portion of the specimen will appear darker because because only few number of electrons gets transmitted, while the converse is, that is the thinner portion appear brighter in the image. And elastically scattered electrons. So as the incident electron interact with the atoms in the specimen, it gets scattered in an elastic fashion, that is there is no loss of energy, and as a result they get scattered and they obey Back's law of scattering, Back's law of diffraction as well, and therefore when incident electron interacts with the atom, atom in the same atomic plane gets scattered by them, and these same angle scattered electrons form spots in the diffraction pattern. So this elastically scattered electrons From that we can extract information about the orientation, atomic arrangements and phases present in the specimen. Inelastically scattered electrons, during the scattering process they lose energy, and this loss of energy is characteristic of the bonding state of each element. So it is used in electron energy loss spectroscopy, and also it forms Kikuchi bands, which is nothing but alternating dark and bright lines, which relates to the atomic spacing of the specimen. So from these three we can extract information about the specimen. So Max Knoll and Ernest Ruska, they are the pioneers of developing the electron microscope in 1931. And transmission electron microscope is an important and unique tool in characterization techniques and in characterization of materials, crystal structures, microstructures simultaneously by diffraction and imaging techniques. That is the main advantage. We can get image as well as we can get the diffraction pattern. So it works similar to a slide projector, where the slide is well illuminated and collimated by this lens. The light falls on the slide and the image is magnified by a magnifying lens and it is projected. Similar to this, in electron, from the electron gun, electrons are coming and it is condensed by the condenser lens. It falls on the specimen, gets transmitted through the specimen, it is magnified by a lens and it is projected on the screen. So this basic TEM instrument possesses a highly evacuated metal cylinder. It is why do we have a vacuum? Because only in vacuum electrons can move freely. Therefore, the entire metal tube has to be highly evacuated. And we have in electron gun we have tungsten filament, that is cathode, and there is a metal plate with the central aperture which is acting as anode. So the electrons from the cathode are accelerated towards anode, and there is an applied potential is applied to the tungsten filament, and therefore the highly energetic electrons then can pass through the magnetic lenses and it hits the target and it gets transmitted through the specimen and it is projected on the fluorescent screen. And then otherwise we can have a photographic plate. This is a ray diagram of a TEM where it consists of electron source, condenser lens, condenser aperture, sample, objective lens, objective aperture and projector lens. This is the basic layout of transmission electron microscope. Now the main part here, imaging and diffraction in TEM can be achieved only by placing objective aperture at the back focal plane of the objective lens, and by the diffraction pattern can be obtained if we place selected area electron diffraction aperture at the intermediate image. So the TEM can work as in image mode or TEM can work in diffraction mode only by placing these objective aperture at the back focal plane and the SAD aperture at the intermediate image. So also by adjusting the intermediate lens, the image can be produced. So with this arrangement, the real space, that is the image, can also be transferred into the reciprocal space. That is we can have a diffraction pattern. Both can be achieved in TEM, which is a main advantage of TEM. This is what I have explained. An objective aperture can be inserted at the back focal plane to contribute to the final image, and the SAD aperture can be kept at the first intermediate image. That defines the diffraction pattern. So imaging can be of two types: bright field imaging, dark field imaging. Bright field imaging, we are just allowing the transmitted beam to pass through by placing the objective aperture and blocking the diffracted beam. We can get the bright field imaging. This is the photograph of bright field TEM. Then dark field imaging, here we are blocking transmitted beam and allowing the diffracted beam to pass through, by which you can have the diffracted, that is the atoms appearing as bright, whereas the background is dark. Then this is the diffraction pattern. The incident electron gets diffracted by the atoms in the specimen, and if it is a single crystal, for example the aluminum FCC lattice, here the diffraction pattern is pattern of spots. Then this is selected area diffraction. In this concentric rings indicate it is a diffraction pattern produced by polycrystalline material. And the most important part is the sample preparation for TEM. It is very tedious and it is a stepwise procedure where it involves all these steps: fixation, rinsing, dehydration, embedding in resin, trimming of resin block, and collecting of sections on the grid. So these involves these all these process. That is, after that finally the specimen is of the size 70 nanometer, which are cut with a special knife of cleaved glass, and it has to be kept on a grid. Grid is nothing but a sieve woven from a thin metal of wire, usually nickel or copper, of size 3 millimeter. Imagine the grid has very small size of order 3 millimeter, whereas the specimen itself is 70 nanometer. How small it is! Therefore, to handle this specimen and to prepare a sample, skill is very much required, and also there should be a full commitment and patience. So what are all the advantages and disadvantages of TEM? Let us see one by one. It's a powerful TEM offer a powerful magnification resolution, and it has its wide range of applications. It provides information about element and compound structure, and the images are high quality and detailed. But what are all the disadvantage? It is very large. TEM occupies a very huge room. In our Madurai Kamaraj University at Instrumentation Center, we have a TEM instrument occupying a very big room, and it is very expensive. Maintenance, it need maintenance, laborious sample preparation, and the images are black and white. So now with this, even with this disadvantage, TEM is a important characterization technique which is playing an important role in the field of material science. And but the only difficulty is the sample preparation, and which involves a multi-step procedure. Even a single mistake may lead to a wrong outcome. Therefore, full commitment and patience is required. Skill is needed, and also we must be aware of the fact that the chemicals used for sample preparation is hazardous and dangerous. So with this, even with this limitation, TEM is a good characterization technique used for most of the material scientists. Okay, now I am going to conclude this session by quoting Albert Einstein's quote. It has become appallingly obvious that our technology has exceeded our humanity. Yes, we are very much interested as a material scientist or as a scientist, as a physicist. We are very much interested to see the phases of atom, or to see or separate atom by separate. But are we looking at the neighbor phase? Are we looking at our neighbor phase? Yes, that is the question posed to every scientific community. Thank you. Thank you for listening. Have a good day.